heat capacity, right? What is specific heat capacity? We'll call it as S. Many places they will call it as C, small c, and heat capacity will call it as capital C. So that there is no confusion. In small c and capital C, specific heat capacity will call it as S, and heat capacity as C. So what is heat capacity? Heat capacity is the amount of heat a substance requires to raise its temperature by 1 degree Celsius, right? Right? So it is joules per Kelvin or joules per degree Celsius. Is that clear? Meaning to say, there was a certain body, mass was 10 kgs, temperature was, say T initial was 20 degrees Celsius. I provided heat to it. Okay, I provided heat. How much heat I provided? Say I provided 200 joules of heat to it, and the temperature, ultimately temperature final became 25 degrees Celsius. So can you tell me what is the heat capacity? Is there enough information for heat capacity? Yeah, guys, speak up. Heat capacity of the body. People, don't trouble me, man.
Sir, is it 40?
So 4 joules.
Oh, is it recording? Cool. Yeah, 1 second. I'll get back to the screen. Yeah, who said 40? What's your name?
Sir, Agni.
Who
So I
said
think
4?
it's 4. Kalyani.
Kalyani. So,
Kalyani.
Kalyani, right?
Yes, sir.
Okay. So if you say it is 4 joules, it means if I provide 4 joules of heat, it will go up by 1 degree Celsius, right?
Yes,
This
sir.
is the meaning of heat capacity. Is that clear? Is that clear? So it was 20 degrees Celsius. On providing 4 joules, it will become how much? It will become how much?
21.
21 degrees Celsius, right? Right, guys? On
Yes,
providing
sir.
4 joules, it will become how much? 22 degrees Celsius. On providing 4 more joules, it will become how much? 23 degrees Celsius. So I provided 4, then 4, then 4, then 4 to make it 24, and then 4 to make it 25. So how much joules I provided? 1, 2, 3, 4, 5 times 4. How much is that? How much is that? 20 joules. So on giving 20 joules, it would have risen by 5 degrees Celsius. Is that clear? But that's not the case. It took 200 joules, no? Yeah, Kalyani?
Yes, sir.
So what's the answer? So the heat given is 200 joules, and the change in temperature is 25 minus 25 degrees Celsius, which is same as 5 Kelvin change, because 1 degree Celsius change is 1 Kelvin change. Okay, is that clear? So that is 40 joules per Kelvin or 40 joules per degree Celsius. 40 joules per degree Celsius is your heat capacity. That means you provide 40 joules of heat and it changes by 1 degree Celsius. Okay, guys, you understand the meaning of heat capacity? How much heat is going to change the temperature by 1 degree Celsius. Is that clear? Now, what is specific heat capacity? Specific heat capacity, anybody?
So that's 4 joules. I did MC delta T instead of heat by delta T. That's why I got.
Yeah, specific heat capacity is heat required to raise the temperature of 1 kg of the body by 1 degree Celsius. Okay, so heat required per kg per degree Celsius. Is that clear, guys? So in this case, for the same body, 200 joules is required for 10 kg of the body. So for 1 kg of the body, 20 joules was required. Okay. Now that 20 joules changes the temperature by 5 degrees Celsius. So if you divide by 5, then you are going to get the specific heat capacity, which comes as 4 joules per kg per degree Celsius or per Kelvin. Is that clear, guys? Is that clear? Is that clear? If you have any doubt in the two terms, you ask me, because I'll give you only one question today. So to write the heat formula, we write heat is M into S into change of temperature. If the whole body's heat capacity is given, which is very rare, then ms multiplied is given to you. That means C into delta T is the heat capacity. So heat capacity is ms, mass times specific heat capacity, because specific heat capacity means heat capacity per unit mass of the given body. Okay, so all this is very rare. What is in yellow is very rare, because C hardly they will give you, because it is pretty much useless. It is for a given body, and this is for a given material. Say the body was of iron, so they'll say specific heat capacity of iron is so much. Is that clear, guys? Is that clear? So the other term what you should be knowing before we start doing the question is, what is latent heat? What is latent heat? Anybody? When the state is changing, then heat does not change the temperature. Meaning to say, if you have a body and you are providing heat to it, and this body starts melting, that time, if the body was suppose at a certain temperature, say it was at a temperature of 20 degrees Celsius. This is, say, some butter which melts at 20 degrees Celsius. Then this heat is not increasing the temperature till the body fully melts. Is that clear? Is that clear?
Yes.
Is going into the substance, and say this heat was, say Q was equal to, say, 100 joules. So where is the 100 joules gone? We do not lose energy, right? Those 100 joules have gone into breaking the bonds where the energy was stored in the bond. So you have, instead of a solid, you have liquid. So liquid has more internal energy. So whatever energy was there in the solid U, this liquid will have U plus 100 because that much of heat has gone into this. Okay, that's the internal energy. So the molecules movement, this and that is in such a way, particularly the uh, bonding, intermolecular bonding has totally collapsed. So any which way, we are not going to the chemical level of what is happening. We are just saying that the heat given to the substance is going to change the state. So latent heat is this is like it is like a hidden energy, hidden heat. So latent heat is this into mass. So I like mass into L. Latent heat is how much of heat is required per unit weight per kg. How much of heat is required per kg? Heat required per unit mass to change the state. Is that clear? Is that clear? So if I say latent heat of a certain substance is 80 calories per gram, how do you speak it in your mind in full English sentence? What does it mean? What does it mean? Say latent heat of ice is 80 calories per gram, which is the actual value. Latent heat of ice is 80 calories per gram. So what does it mean? Yes, somebody?
It means 80 calories is required to change the state of 1 gram of ice
Yeah, to
water.
1 gram of water, right? So to change the state of 1 gram of ice to 1 gram of water, 80 calories will be required, which is like pretty much very high heat. Okay. 80 calories means you multiply it with 4.18 and you'll get something like 336 joules is required. Got the point, guys? Is that clear? So the formula for this would be to change the state, the heat required will be M into L. 1 gram requires 80 calories, 10 grams will require 10 times 80 calories. So that is this formula. Is that clear? Is that clear? Okay, so shall we start doing a question on this first? The question would require you, your heat is equal to ms delta T is going to get tested, and change of state, when state is changing, then M into L is going to get tested. Any doubts? So shall I give you a question? Easy or difficult or medium? Yes, guys? Yes, guys? Same, man.
Sir, I think medium.
Okay, medium. There is ice. Say ice is 100 grams. I'll be giving you in grams and calories. Okay, that is how calorimetry started. Okay, it is very convenient unit. You have your the whole thing, whole units with respect to heat and all came with respect to water. Water is melting at a certain temperature, we call it as 0. Water is boiling at a certain temperature under 1 atmospheric pressure, we call it as 100. Then we are giving heat and heating up water, and in the ratio of the heat given, we are just calibrating the temperature scale. And fortunately, the specific heat capacity of water doesn't vary too much with the temperature, so it can be taken as constant. And we said that that constant is the heat required to change the temperature of 1 gram of water by 1 degree Celsius is how much? specific heat capacity of water? If you were the ones who are inventing the units and the heat required, heat is equal to how much to change the temperature of 1 gram of water by 1 degree Celsius? What would you say?
So 1.
Yeah, so they said
So
it
is
is
it what?
so they said it's 1 calorie. Okay, so 1 calorie per gram per degree Celsius. Quite convenient, right? Because they are inventing the unit. So why they should go for any random number, right? Later on, when you have to just relate heat energy with the actual mechanical energy, and the mechanical energy, we have got this guy Newton, and then work done is equal to force into displacement. It gives us a certain unit, and that has to be related. The same work will create the same amount of heat. Then yes, there is a relation that yes, 1 calorie is coming out to be roughly 1.8 joules. But if I'm purely doing heat, then why should you even I do it in joules? Okay. That would have been the thought of people say 50 years back. Okay, so I'm 50 years old, so I'm just going to do that way. So ice is 100 grams. It is at a temperature of suppose minus 10 degrees Celsius. Okay, or I'll just say minus 20 degrees Celsius. Is that okay, guys? Then there is water. Say 5 grams. Okay, and it is at 5 degrees Celsius. Is that okay? Is that okay?
Yes, sir.
Find the final temperature when I mix the two. Okay. Now, what's your approach? You have ice, you have water. One is at minus 20 degrees Celsius, one is at 5 degrees Celsius. So we have to figure out that ultimately it will be fully ice or fully water or what, right? Is that clear? Is that clear? Water is going to give the heat to ice. So heat taken by ice is heat lost by water, right? So ultimately you have to write equation something like heat is equal to heat. But you'll be able to write it if you have a picture of ultimate temperature is what. So what do you think is the ultimate temperature? 0, positive or negative? What do you say? Guys, anybody there?
So is it negative?
Yeah, so it cannot be a hunch. So can you tell me why negative? Who are you, by the way?
Avni.
Apni. So why negative?
Sir, because of average temperature?
No, not at all. Oh, by the way, I did not give you specific heat capacity of ice. Anybody?
1/2.
So
Yeah, 0.5 calories. This is luck, okay? Water is 1. Ice being half of it is luck, okay? Almost half of it. And then latent heat capacity of fusion. Fusion, that means ice becoming water, is massive, 80 calories per gram. Okay, therefore iceberg floating in sea, they keep on floating, they just don't just melt away and all. Okay, so tell me why it is negative. So the point is we have to have a very methodic approach, and therefore the next question which I give you, you should not be doing it wrong, and I'm going to show you the method what you should be following. Is that clear? Ice from minus 20 degrees Celsius, suppose it was going to 0 degrees Celsius and it was melting. Suppose that was happening. Okay. 1 second, I'll just draw in a new layer. Yeah, what did I say? Ice from minus 20 degrees Celsius, suppose it was going to 0 degrees Celsius. It would have taken how much of heat? In the journey of ice, how much of heat? We'll just keep
1000 calories.
So we'll say, okay, we'll do a ms delta t. This is useless calculations, okay, because we don't know if this is happening or not. But we have to do some useless calculation to actually get the picture right. Is that clear? That's the key, okay? That's 100 grams per, how much is, multiplied with how much is specific heat? 0.5 calories per gram per degree Celsius. And how much is the change in temperature? 20 degrees Celsius, right? So we first cancel the unit, degree Celsius, gram gets cancelled, we are left with calories. So how much is that? How much is that? 0.5 into 20 is 10 into 100, 1000 calories. Is that clear? So somebody has to give him 1000 calories to actually go to 0 degrees Celsius. Okay, then who is the guy who can give? Water
So
can fall
water-
down in temperature, right? So let us see the journey of water. So water goes from, suppose it is going from 5 degrees Celsius to 0 first. Let us see how much of heat it can give. Yeah, somebody tell me how much can it give?
25 calories.
Yeah, how much was the weight? 5 grams. The mass was 5 grams into 1 calorie per gram per degree Celsius into what is the change of temperature? 5 to 0, which is 5 degree Celsius. Is that clear? So which is 25 calories, right? Which is too less, right? Hardly anything to give. Is that clear? So obviously, while this has given 25 calories of heat and water has reached 0, ice would have reached somewhere some negative temperature, but not 0 for sure, right? Right? Because it requires 1000 calories, right? It would have just shifted by a little amount. Is that clear? Is that clear?
Yes, sir.
Yeah. After that, so we have water has got more heat to give because it can freeze and it can lose the latent heat, right? So suppose water from 0 degrees Celsius becomes 0 degrees Celsius ice. How much of heat it can give now? How much of heat it can give now?
Sir, is it 975 calories?
So how much is the water? The formula is M into L. How much is water? 5
So 400.
into 80, right? Is the L, right? ml. So how much of heat? 400. Now this is massive heat, but still less than 1000. So the total heat water can give is 425 calories. Is this part clear, guys?
Yes, sir.
Clear? Hmm? Is it clear, people? So what is the story? We are just doing this rough calculation and this is not going to help you much except for framing the story. So what is the story? What can be happening? The ultimate temperature is a negative temperature. Why? Because water from 5 degrees Celsius coming to 0 degrees Celsius gives only 25 calories. After this, 0 melting to 0 degree water, still the journey of water, becoming 0 degree ice gives a 400 calories, wherein the ice required to reach the 0 from minus 20 required to reach the 0 was too much. How much was that? 1000, right? That means it has never reached 0 and there is somewhere over here that water is also reaching and ice is also reaching. So there is some temperature over here. Is that clear? And that temperature is say a minus T degree Celsius. Is that clear? So if this picture is clear, then only you will start working in the question. Got the point, people?
Yes, sir.
Now can you work out the question? Can you work out the question? I'll write it in the language because I'm doing this question. Next question I'll not do for you. You don't have to read what I'm writing and you can do your work. Once they are both at minus 3 degrees Celsius, nobody is giving anybody heat. No exchange is happening because same temperature has been achieved. When temperature is same, there is no heat transfer. Heat transfer is always because of change in temperature and difference in temperature, I should say. Okay, guys. So heat taken by ice to reach minus 3 degrees Celsius. So who can tell me the mathematical form of this first line? Name your name and then you speak. Mathematical form of this. Who will speak? Heat taken by ice to reach minus T degrees Celsius. Yeah, speak up. Heat taken by ice to reach minus T degrees Celsius from minus 20 degrees Celsius. Speak up.
So 50 into 20 minus T.
Name first.
So suction.
So it will be ms delta T, right? This formula, right?
Yes, sir.
So how much is the mass of the ice? 100. Yeah, speak up. Then
1 by 2.
yeah, 0.5 is the S and delta T is how much?
So 20 minus T.
Yeah, that is correct. 20 minus T. It's minus T is the higher one, by the way. So it is minus T minus 20. Minus T is the higher temperature, minus 20, which gives you a 20 minus T. Okay. Okay. And I'm going to get a T as something like, say, T is equal to 8. Means my final temperature was what? Minus 8 degrees Celsius, because I've already written a minus T over there. Okay. One could have written a T over there. And if you had not written minus T and you had written T, then it was T minus 20, which is equal to T plus 20. So you could have written a T plus 20 also over here. T plus 20, which is also correct. That time we'll get T as a negative answer. it will come as a -8 or something. Is that clear? Is that clear? Okay, who will tell me this heat given by water to reach -T degrees Celsius? That thing. Who's going to give me this journey? Yeah, just speak it out, man. Fast. Fast, fast, fast. Fast.
So 5 into -t minus 5.
No, 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 no. Absolutely wrong. So heat given by water to reach -T. That happens in 2 steps, right?
So 5 into -5 plus 5 into t minus 5 plus 400.
Yeah. This happens in 2 steps, right? 5 to 0. No, that is also wrong. Okay, okay, guys, write it. Take your time and write it. I think you are going to write it wrong because you are telling it wrong twice. Water goes to -T. It happens in 3 steps, I would say. It goes from 5 to 0. Then at 0, it melts. Sorry, at 0, it freezes. And then once it has frozen, that frozen ice, which was earlier water, that goes from 0 to -T. Right, guys? Right, guys? That is what has
Yes, sir.
been established. So therefore, we were doing that hard work. Otherwise, we would have written any equation over here. The point is, any equation doesn't work. You have to write it the right equation. So you should know what is the final state. So who can say 3 things have to come? 1, 2, 3. If 3 things you can write correctly, water going from 5 degrees Celsius to 0 degrees Celsius, then freezing, then that water which has become ice going from 0 degrees Celsius to -T degrees Celsius, right? That's the journey, no? That is why we did that hard work. This hard work was to establish that, yeah, this is happening and ultimately it is reaching a -T degrees Celsius over here. Okay? All the hopping was also shown that it went from 5 to 0, 0 it melted, and some calculations are also written, so the same repeat calculation is going to come, but then it goes to this -T degrees Celsius. We have written this part. We have written this part. That ice came to -T, left hand side. The right hand side, which is in 3 parts, we are yet to write. Is that clear, guys? What's going on? So write it. So we'll say one part at least, first part, 5 to 0. What is it? It's a change of temperature. So the formula of ms delta T should follow, right? Change of temperature ms delta T follows. Okay. So what is that?
Sir, it will come out to be 25 calories.
Yeah, 5 into S is 1 into delta T is 5 minus 0, which is 5. Who will tell the second part? It is M into L. So 5 into 80. Who will tell the third part? Or the third part?
So 5 into -t.
So 0 plus T into.
Yeah, speak the name and tell.
Sir Kalyani,
Kalyani, tell me.
is it 5 into 1 into 0 plus T? So into T.
No, 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 it is not.
So Saksham.
Yeah, Saksham.
So 5 into -t.
That's absolutely wrong. That is no formula at all. That is none of
Sir, is it
and one second, Saksham. How is that? mass into temperature is which formula, man, of heat?
So, but
There are
S
only,
is 1. So 5 into minus T by 2.
so S is 1, then the lady before you, Kalyani, also said the same thing then.
So no, S will become 1 by 2 because it's become ice now.
Yeah, so you have to say that, no?
So yeah, I said that the second time.
Yeah, absolutely last time after poking. Anyways, 5 is, now it is ice, right? 5 grams of mass will become 5 grams of ice. So ms delta T. Half is the S and delta T is from 0 to minus T. So 0 minus T, which is a T. We ensure that, okay, if T is a positive number, T is a positive number. The temperature is minus T. T is going to come as 8 or something. The answer is going to come as minus 8. Okay, T is a positive number. So we ensure that we have positive terms. Okay. Is this a positive term? Absolutely it is. T is going to be something, some number less than 20. It's a positive term. Okay. So be sure that you are writing positive terms and you are not messing up with the algebra over here. So that gives you the answer. We don't have to calculate, but let's just calculate. Okay. 25 here, 40 there, and 5T by 2 here, right? What over here? We have 1000 minus 50T, right? Right, guys? Right, guys?
Sir, I had a doubt in the previous step that when you're taking 5 into 1 by 2 into T, why is it not taken as minus T?
See, it is higher temperature minus low temperature. Change of temperature is higher temperature minus low temperature. 0 degree Celsius minus T degree Celsius. Okay.
Okay, sir.
Other thing is, even by mistake you write minus T, you ensure that you are writing positive terms. Okay. If I said my final temperature is T, then obviously I have to write a minus T. Okay.
Yes.
I said my final temperature is T, which is a minus 5 or something, but T, I'm calling it as T, which will turn out to be minus 5. Then I will write it as minus T. My minus T will be positive that time because T would be a minus 5, minus T will be positive. But then this also becomes a plus over here. Okay. Why plus over here? Because 20 minus, sorry, higher temperature is T, T minus 20. Minus 20 was a lower temperature. So it is a T plus 20. Okay.
Yes.
So both places it will change. Okay, anyways, coming back to this. So what is this? What's the calculation? You have a 50 and so 52.5 T.
Here are some pictures that match.
This is okay. If this goes on the other side, what it is? 575. Right? Right, people? So when you divide the two, what do you get? So you can do the division. I'm not doing it. So T is equal to 575 divided by 52.5. So somewhat like 11 it is coming. Right, guys?
Yes, sir. It's 10.95.
Slightly short of 11 it is coming. I'll just call it as 11 just for the sake of it. Okay. So 11 number. I'm not even writing delta C over here. Okay. Why? Because you see, I've written minus T delta C. So I'll substitute, my answer is minus, and then instead of T, it is the 11 which is coming, delta C. Sorry, degree C. So that's my answer. So which was, my story was correct that the ice is going to a certain level, but it is remaining in the negative. But the point, Had it been that ice was becoming water, the equations would have been completely different. Don't think that a minus and plus is going to change. The equations itself becomes different. So before you write the equation, the story has to be clear. If it is not clear, you will not get the answer right. Is that clear, guys? If you have any doubt, you ask me, because I'm going to give you a question where you may get stuck if you are not clear with the story. Is that clear? Is that clear? Is that clear?
Yes, sir.
Okay, shall I give now? Shall I give?
Yes, sir.
Others, ready, guys?
Yes, sir.
Cool,
Yes.
cool, cool. It was 20 grams of ice. Is that clear? And same thing. So I'm putting a really simple picture in front of you. Okay? Do it then. $20 grams of water. Okay? And same story. Yeah, done, guys? Done, guys? Done, guys? So this is a little tricky. You have to figure out what happens. Okay? So could anybody figure out what happens? Forget about the final
Sir,
question. Hmm?
The energy required to convert water to ice is not enough, so it will remain at 0 degrees Celsius.
Okay, what about like ice fully melts and becomes water?
Sir, that's not possible because to convert ice to water, we need 1000 calorie, and to convert water to ice is just 100 calories. So there's a huge difference.
To convert what ice to water, what do we require?
1000 calories.
1000
Sorry,
calories.
1000 calories is to convert it to 0 degrees Celsius, and
And
then
then
from zero to water, it will be ml. That will be 100 into 80. Yeah, 8000 calories.
1000, right? So totally 9000 is required, right? Hmm?
Yes, sir.
Which is not there, right? Hmm?
Yes, sir.
Okay, so you start doing the question now. Okay, you got the picture what has to happen. Now you start doing the question. Others, those who have not got the picture, whatever you write as the equation, some ms delta t here, some ms delta t there, you'll get a wrong answer. So it will be a waste of time even if you start doing the question. So you don't do that in the test paper also. You only do when the story is clear. So others, apart from the last student, who was the last student who said what is going to happen?
Sir Haley.
Okay, apart from Haley, anybody else has any story? Is the picture clear? See, three things can be happening, and you have to test out that the tire something that without even having any relevant calculation, your rough calculation will be longer. You'll have to test out three things. What are the three things? If you can see, we were testing out, we tested out one thing, and fortunately, this is what was happening. So it was good for me. And this calculation of testing out perhaps was longer than the actual equation which I wrote. The actual equation was simpler and shorter. Okay, maybe. Okay, testing out may be longer. Okay. So what are the three possibilities you have to test out? Tell me, guys. At least have that much of clarity that what you have to do. One, everything becomes what? Ice, which was the previous case. Everything became ice or not? Final temperature was everything rested at minus 11 degrees Celsius. Is that clear, guys? What's the other possibility? What's the other possibility, people? What's the other possibility?
Everything becomes water.
Yeah, the ice melts and becomes water. Oh, this is Haley again or what? Who said this?
No, so it's ugly.
Okay, good. Apart from you two, somebody else say something, man, and then there's one guy who's speaking. What's the third possibility?
So when it stays at zero and both water and ice coexist.
Yeah. That everything is at 0 degrees Celsius and there is some ice and there is some water. This has got two situations. It can happen in two ways. What are the two ways? Say ice reached zero first and started melting. What is the other way?
So water
Water
reached
reached
zero
zero
and started
first
freezing.
and started freezing. Is that clear? Ice started melting or water started freezing. Now you take your time. Okay, I've got a lot of time. I'm not going to give you a calorimetry question unless until you do this without the calorimeter present. Calorimeter is a container in which you'll be putting all this. So make rough calculation and ensure what is happening of the four things. Is it the first? Is it the second? Or is it third one or third two? Okay. One of the four things is happening. Is that clear? Is that clear? Yeah, Haley, in the third one, what was it according to you?
Sir, I think the water starts freezing.
Okay, are you sure?
Yes, sir, because the heat required to.
No, because start doing it then.
Okay.
Okay. Haley is writing equations according to this. If you are writing equations according to this, it will not match when you write equation according to this or this or this. So that is the sad part, that you have to know the story. Is that clear? In some of the other physics chapters, you may think that, okay, the block was moving this side. You write equations, ultimately your answer comes negative, and you come to know the block was moving other side, but your equations don't go wrong. But in this case, it doesn't happen that way. If you don't write the equations according to what is happening, your equation will go wrong. Okay, so we really hope that Haley is writing equation according to the fourth one. So we hope that she has got it correct, the situation. I'm not endorsing her situation, what she got. Others? If you want to ask me how to do, if you want to go back to earlier question that, sir, what are you doing there? I can show you all of that. Okay, why did you do this? Why did you do that? If you ask me, I'll show you all of that. But the fresh question, try to do yourself. Watching another question being done by somebody else doesn't help you. This was the first question. Anybody wants any help? You have to open your mouth and you have to ask. Again, opening your own mouth is your own initiative. Nobody else can come and open your mouth. Yes, guys. So nobody else is working on the thing except for Haley. So this today's session is of no use to at least the rest of you. If 25 of you are there, then 24, it is no use. I'm not saying that you should be able to do it. What I'm saying is you should be at least asking that, sir, what you did in the earlier one, how is it related? I don't even know where to stop my screen. In the earlier question or the fresh question, I don't even know. Because nobody's saying anything. I was really disappointed when these so many batch 1, 2 guys just came in and they were speaking. I thought that the ones who had to ask where it is really needed, they'll not be able to speak. Now today they are not there, and it is even worse. At least when they are saying you are learning something from their doubts, you are not saying anything from your own side. If you don't speak, how will you learn? If I look at the positive side, I think all 24 of you who are not speaking should be doing the question and get the answer right. And hence you're not speaking. But I would have liked to verify before you are working out. That is like being too positive of the situation. Yeah, so anybody got the answer? That what is the situation, Ellie?
Sir, I'm trying to figure out, like I'm between of solving. Like
Anybody
2-3
else?
minutes, I'll be able to solve.
Okay, I'll wait for you then. And then I'll solve. By that time, when I start solving, if any, others have not given an input, they may discontinue from the meeting, and I'll just tell Haley the answer. Others can watch the recording later on.
Sir, could you explain how you got again water started freezing among the two?
What?
How did you conclude that the situation is water started freezing?
No, this Haley has concluded. I'm not endorsing it. You have to come to one of the three conclusions by doing some rough calculations. So what will you do? So you'll imagine all the three situations. You'll say that, okay, everything becomes ice. Okay, or everything becomes water. One of the better ways of coming to a conclusion is doing some rough calculation of all the ice going to zero is how much of heat. One calculation for your own sake. Then all water going to zero is how much of heat. Okay, disrelated, unrelated. Okay, unrelated scenarios. Don't start relating. Okay, just have some calculation that okay, so much calories, so much calories. All ice melting to 0 degree water is how much of heat. Okay, all water freezing to 0 degree Celsius, ice, is how much of heat. These are four rough calculations which you should have to conclude that what might be happening.
Yes, sir, I think I got an answer. I
Wait,
think
wait,
water
wait,
conver-
wait, wait, wait.
Okay.
What? No, wait. Others? Are you willing to do these four calculations and doing some analysis? 11th and 12th will not be about you being able to apply some formula that mass was 10, S was 1, T was 20, I can multiply. This is not the job of multiplying numbers, is not the job of a science person. What you're doing, you should be knowing. I really don't know how to carry forward from here because nobody's speaking anything. So I'll just ask. I hope you'll speak out at least this answer. If the whole of 100 grams, the whole of 100 gram ice went from minus 20 degrees Celsius to 0 degrees Celsius, this means how much of heat it required? Tell me somebody. Give me the number.
Sir, 1,000.
No, not Haley and the other girl who said.
Sir, I got 1,000.
What's your name?
Bhavya.
Huh?
Bhavya.
Bhavya. Okay, so it will be 100 into half into 20, which is 1000 calories, right? This is one calculation just for my sake. Okay. Other calculation. The full ice melted from 0 degree to 0 degree water. What is the heat?
So 8,000 calories.
Okay, 100 into 80, which is 8,000 calories. Absolutely right. Now, some calculation for the water guy. So, for the water, so water was how much? 20 grams. 20 grams of water went from 5 degrees Celsius to 0 degrees Celsius. How much of heat? How much of heat will it give out?
So is it 100?
Now, why any doubt? MS delta T, 20 into 1 into change of temperature 5, which is 100 calories. Okay. And the last rough calculation for my own sake is if water had to fully melt from 0 degrees Celsius, that 20 grams of water had to, freeze from 0 degrees Celsius to 0 degree ice, then how much of heat will it give out? Hmm? Yeah,
1,600.
20 into 80, right? 1,600. So these are 4 numbers in front of me. Okay. Now with these numbers, you have to apply. So you have to start using your brain now. Okay. I'm saying this calculation is just like a routine clerk kind of job you do. That straight away you get these numbers. Then what does it mean? So you have to apply. So you have to think who is racing to 0 first? Is anybody racing? Somebody must be, right? If you cross over to water side, then ice must have raced to 0. If everything cross over to ice side, then water must have gone to 0. So something would have gone to 0, right? So who is reaching 0 first? For that, you have done a calculation of ice reaching 0 requires how much of heat and water reaching 0 gives out how much of heat. So what do you think? Who is reaching 0 first?
Ice.
Others? Who is reaching 0 first?
Sir, water.
Ice required 1,000 calories to reach 0. Okay. And this heat is just taken by one and given by the other one. Water is giving, ice is taking. There is no third person present over here. Okay. So while water is giving, ice is taking. So while water reaches 0, it gives us how much of heat?
So 1,000. So water.
Yeah,
So 100 calories.
it gives out 100. With that 100, does the ice reach 0?
Oh, no, sir.
No, it required 1,000, right? Right.
Yes, sir.
So it is somewhere in the negative, big time negative, perhaps minus 15 degrees Celsius or something. Is that clear? Is that clear? So who reaches 0?
900. Ice.
No, you are again saying ice reaches 0. Why you are saying that? Let me hear out.
Because ice has like a larger mass.
So that's the reason it is not reaching 0 first, by the way. But your mass, specific heat and temperature, everything taken into account, you have calculated a certain number. It's not only mass which matters. It is not only specific heat capacity which matters. Somebody would have said something else because water has higher capacity. OB alone is not the right answer. Does this number, can you give me a sentence with this number? What does this number mean? Can you speak this number in a sentence?
So
Point 1, can you speak in a sentence?
So 100 grams of ice requires 1000 calories of heat to go from minus 20 degrees Celsius to 0 degrees Celsius.
Absolutely right. Well said. Okay. So somebody has to be giving the heat. Do you know who is the person who is giving the heat in the whole story?
Water.
Yeah, the one which is hotter is giving the heat, and water is hotter is giving the heat. Okay. Are you given point? So can you speak this sentence?
So
So 20 grams of water goes from 5 degrees Celsius to 0 degrees Celsius and requires 100 calories of heat.
Not requires. That's wrong sentence.
So it gives out
Yes.
100 calories of heat to go from 5 degrees Celsius to 0.
0 degrees Celsius water, right? So ice required 1000. Ice required from minus 20 degrees Celsius coming to 0, it required 1000. So would it be coming?
No.
No, it is getting only 100. So it will be stuck somewhere over here, right? Right? While the water has reached 0, ice would be here. Lady, though the girl who was asking, are you getting the point what I'm trying to say? If not, I'll repeat again. Obviously in a different way. Yeah, who was the lady who was saying, who spoke out the sentence correctly?
So Kalyani.
Yeah, Kalyani. Kalyani, ice takes 1000 calories to go from minus 20 to 0. Get the point?
Yes, sir. I didn't answer that. I just told the sentence.
Yeah. So water is giving it, water is the one who is giving the heat, and water is not able to give the heat of 1000. Okay. So while reaching 0, it gave out 100. So when simultaneously, if we work out, then when water has reached 0, ice would have taken some 100. We don't have to calculate, but for your sake, I'm just calculating. It would have taken the 100 calories, same 100 what water is giving out, and would have reached some temperature T. And if I want to do a quick calculation, it would be 100 heat taken by ice. So ice was 100 grams into delta T. Okay. And ms delta T. So what does the delta T come? What is the delta T? Delta
2
T is 2.
degrees.
That means it would have changed by 2 degrees Celsius. That means it would have reached minus 18 degrees Celsius only. While water has come to 0, ice has gone to minus 18 degrees Celsius only. Okay. Ice is hardly changing because ice is so much massive. Ice is 100 grams, water is just 20 grams, 5 times less. Are you getting the point? So this is the simultaneous calculation, which you don't have to do. You don't have to get the minus 18 degrees Celsius. So one thing is concluded, that ice is yet to reach 0 and water has reached 0. So now what will naturally happen? What will happen then?
So water starts to freeze.
Yeah, water starts to freeze. So we'll say water starts to freeze. So it can happen. Now two things can happen. Either scenario number 4, water starts to freeze, or this thing that everything becomes ice, like water fully freezes. Okay. Get the point? So one is, it is like part ice, only part is freezing, fully freezing. So water starts to freeze. So we'll come to our calculation of number 4. Calculation number 4. And what does it mean? If water had to fully freeze, it gives away how much calories?
1600.
Yeah, so somebody has to take it. Is the ice willing to take 1600? No.
Yes.
It is just willing to take how much more? How much more? 900 more. Why 900 more?
1000 minus 100 is 2,
Yeah,
please.
because with 1000 it reaches a 0. Get the point? So ice will take till ice is less than 0 degrees Celsius. Once they come at the same temperature, it doesn't take heat. 0 degree ice will not take heat from 0 degree water. It is not going to take it because both are at 0 degrees Celsius. So while ice was enjoying a negative temperature, only till that time water can give. So we conclude that the full water cannot freeze, because if full water freezes, it will give 1600 calories of heat, but there is nobody to take that 1600 calories of heat. Ice is going to take only 900 calories of heat after it has reached a minus 18, or even if I take the whole thing, ice is going to take 1000 calories of heat from water. So in no case it can take the 1600 calories of heat. Is that clear? So that concludes our story. So what is our story? So we say our story must be that water reached 0 degree Celsius first. Any doubt in this? You ask me right now, anybody. Next line. Since it has reached 0 degree Celsius first, water started freezing, right? Only partly water got frozen. Do you understand the last part? It fully did not freeze because fully freezing, much before fully freezing, ice reached the 0 degree Celsius, and hence it could not fully freeze. This goes to your head fully, then only you will be able to write a logical equation. Okay, since the time is up, I'll write the logical equation. From the ice side, ice went from minus 20 to 0 degree Celsius. So it is M, which was 100, into S, which was half, into change in temperature, which is 20, positive number 20. This is the ice side story, who's taking the heat. And water is giving the heat. So from the water side, what it is? 1, it went from 5 degrees Celsius to 0 degrees Celsius. So 20 grams. 20 grams into S into change of temperature 5. It became 0. Then some of the ice melted, has frozen. So some of the ice, so say M mass of the ice has frozen. M into 80. While this is happening, ice has become 0 and nothing happens. So this is the equation. And I'll really pray to God that this M comes less than 20. If it comes more than 20, that means my equation has all gone wrong. Some of the ice, out of the 20 grams, some have frozen. Is that clear? So we do the calculation. So what is the calculation? This is 1000. This is 100. I'll write it first. 100. And this is 80. So my M is 900 worth of calories. In my storyline also, 900 worth it could have taken. 900 by 80. Is that clear? So 90 by 8. So how much is that?
11.2.
Yeah, it is 11 and then a 2 by 8. 11 or 2 by 8, no? 0.25, no? Okay, guys, which is less than 20. So your final answer is that you have a mixture of ice and water, where you have water. How much of water? How much of water? 8.75 grams of water. And how much of ice? How much of ice? 111.25 grams of ice. 100 grams of ice already, and then more water has gone frozen into ice. So if you can imagine the picture, there was a big block of ice on which you have put water, which was not a very hot water. Some water you pour, and that water also froze. 11 grams of that water froze, and some of the water remained. That is what happened. Okay, is it clear, guys? Is it clear? So
Yes,
try
sir.
to do both the questions yourself, and I hope you understand that calorimetry is a very simple equations, very simple equations, but without the right picture of what is happening, it is lethal. Okay, is that clear, guys? Self-destructive if you write equations without the picture. Okay. Chalo.
Yes, sir.
So stay back. Rest may go away. Bye bye.
Sir, I wanted to understand about water equivalence.
Okay, now the time is up, but I'll just tell you very fast. Anybody else? Anything else? If we do a calorimetry question, I could have done that. See, this is a calorimeter. Okay. And suppose it has got some water. Are you there, lady?
Yes, sir.
Yeah. Nice water I'll make. Okay. Say water is mass is equal to say 50 grams. Specific heat capacity of water is 1 calories per gram per degree Celsius. Okay, guys. Now this container has got a mass of suppose 20 grams. Suppose, okay. If so much of water is there in that, this mass will be like much more. Okay, 200 grams or something. But I'm just picking it up. Mass is suppose 20 grams, and specific heat capacity of the calorimeter material, mostly copper. Okay, and I don't remember the specific heat capacity of copper, but I'm just writing it as roughly 0.2 calories per gram per degree Celsius. Okay, we know it is much less than water. Is that clear, guys?
Yes, sir.
Okay, now what you do is generally you will be dropping some kind of metal in it, which was having a certain M, certain S, and certain temperature, and it will come to a equivalent temperature later on, right? So, okay,
Yes.
let me do that way itself. Okay, so you drop a certain mass. So earlier, the temperature of this setup, the whole setup, temperature was 20 degrees Celsius. Okay. Then you drop a certain mass, and that mass is equal to say 100 grams. The specific capacity is what you are trying to find out, which is the general experiment with the calorimeter. Okay, many a times. What all things you can note is the temperature. So the final temperature became some 25 degrees Celsius because a hot body was dropped. Initially, the temperature of that body was T was equal to say 50 degrees Celsius. Okay, is that clear?
Yes, sir.
After everything is settled, at equilibrium the temperature is 25 degrees Celsius. Now propose me equation very fast. So I'll tell you since the time is almost up. So heat lost by the metal, which is mass of the metal into S of the metal into change of temperature of the metal, must be equal to heat gained by the water, S of the water into change of temperature of water, okay, plus heat gained by the container also, right? The container will also gain the heat, right? It is water in the container. So mass of the copper, S of the copper, and delta T of the copper and of the water will be always the same because they are always, it is quite conducting at copper and is always at the same temperature as what water is. Is that clear? Is that clear?
Yes, sir.
So calculation wise, we'll be writing something like this. That 100 into S into, yeah, tell me what is this delta T, people? 25
25. Yeah.
is equal to M of the water, which is 50, into S of water, which is 1, into what is that delta T? 5.
Yeah.
Is that clear? Plus M of the copper, which is 20, S of the copper, which is how much?
0.2.
0.2 into the same 5. Is that clear?
Yes, sir.
Now comes water equivalence. Okay. So I hope this calculation is okay with all of you, right?
Yes, sir.
Okay. So if I take 5 common over there, what can I say? I'll take 5 common. And it is this into 5, right? Right?
Yes, sir.
Okay. So this 20 into 0.2, I could have said that this vessel, it is as good as so much of water. This vessel, the heat capacity of the vessel is as good as so much of water. How much will it be if I say that?
Yes, sir. Can you repeat it?
The 20-gram copper vessel is as good as, okay, it changes its temperature by 1 degree Celsius when you give so much of heat. So it is as good as so much of water. How much of water?
I think it's 50 grams itself.
No.
20 grams.
Reframe my question. Okay, this is a copper vessel. Okay. I will make a little thick one. Ayyo. Okay, so this is your copper vessel. Get the point?
Yes, sir.
It changes its temperature according to heat is equal to mass of the copper vessel into S of the copper vessel into delta T, right?
Yes, sir.
So if I give it if if I say this copper vessel was 20 gram copper vessel, its specific heat capacity was 0.2. Okay. And if I give it, say, 100 calories of heat, how much of temperature it will change by?
25.
Okay, very good. So it is going to change by 25 degrees Celsius, right? Right.
Yes, sir.
Now, if I say instead of this copper vessel, I had an imaginary water vessel. Okay, imaginary. Okay, such that when I give 100 calories of heat, that water vessel also changes by 25 degrees Celsius. By the same amount it changes. So what should be the weight of that water vessel?
What was the S of the water vessel?
S is water says
Okay, yeah, 1.
1. Yeah,
So it will be 4.
it will be 4. Is that clear?
Yes, sir.
So we say that 4 is the water equivalent for this copper.
Okay.
This 20 grams of copper is as good as 4 grams of water. Okay. Now the full thing is that you had water in this and all. So you'll do a calculation of water changing heat, ms delta T on water you'll do, right? Ms delta T on water you'll do, and you'll do a ms delta T of the copper, right?
Yes, sir.
But when we equate, we somehow say that this water equivalent is certain m dash, then we can do the ms delta T of water and the vessel together as if it was a water vessel. Okay, as if it was totally water. So temperature is changing by delta T. So this water equivalent is say 4 grams and the water inside is suppose whatever 50 grams or whatever. So instead of doing it in two parts, that 50 into 1 into delta T plus copper ka what was it, 20 into 0.2 into delta T, we do in a single go as 50 into 1 into delta T plus 4 into 1. You yourself said the number 4. Okay, 4 into 1 into delta T. So the good point is 1 into delta T and 1 into delta T is common. So it is as if it was 50 plus 4 grams of water, which is changing the temperature from whatever T1 to T2. Okay. So it is as if considering the vessel and the water together as if it's a single thing. Hence it is called water equivalent. What's the point?
Yes, sir. So basically, you're finding the equivalent weight of water of the copper and then just adding it up.
Yeah. So the by formula it will be mass of the actual material of the vessel into specific heat capacity of the actual material should be equal to imaginary water weight into S of water. Okay. Only helpful when the calorimeter was having water inside it, so that you can consider the vessel and the water together. Is that clear?
Yes, sir.
So in the previous calculation, this 20 into 0.2 can be replaced with water equivalent into whatever water equivalent they give you. So in this case, you calculated 4 for yourself. This can be replaced with water equivalent into 1. Is that clear?
Yes, sir.
So generally they will say it was of a material of brass or whatever, but they will say water equivalent. So you don't have to wonder about, oh, what was the mass of the brass, what was the S of the brass. No, you don't have to, because that will be equal to the water equivalent given by them into S of water. Okay.
Yes, sir.
MS gets, so you can write, you are always welcome to write the MS of the actual thing, but then later replace it with the water equivalent. into S of water. Okay.
Yes, sir. Got it.
Okay. Anything else? Anybody else?
So there's no one else in the meet.
Oh, everybody knew. Only you don't know water equivalent, huh? Bye bye.
Bye, sir. Thank you.
Thank you.